This is my favorite problem in this homework set. It's problem 53. It said, early skeptics of the idea of a rotating Earth said that the fast spin of Earth would throw people at the equator into space. So the radius of the Earth is about 6,400 kilometers. Show why this object is wrong. Show why this objection, is wrong by calculating A, the speed of a 97 kilogram person at the equator, the force needed to accelerate the person in this circle, the weight of the person, and the normal force of the person, force of the Earth on the person, that is the person's apparent weight. You actually are a little bit lighter at the equator. You feel a little bit lighter at the equator than you do here at, like at the North Pole or something. So let's write down what's given. This is number 53 on page 173. So here we've got the Earth. Let's look down on the Earth. This is what's given. We're looking down on the Earth from the North Pole. Here's the North Pole. And here's our person on the equator. We'll just draw him right here. Standing on the equator. Obviously not drawn to scale. All right. And this person is moving in a circle. Now the radius here is given to be 6.4 times 10 to the 6 meters. I'm just going to do the unit conversion for you real quick. That's our radius, r. And what's the period? They didn't say what the period is, but how long does it take to go all the way around this circle one time? 24 hours. So the period is equal to 24 hours, which I believe is, it's 1 day, but it's 84,600 seconds. Is that right? Those of you that did this problem, how much time is that in seconds? $84,600 seconds in 1 day. Okay. Oh, I'm sorry. Okay. 80 what? I knew it was one of those. Okay. Quiet, please. So, here's what we're trying to find. A, we want to know what is the velocity of the person standing there at the equator. Oh, let me zoom out. Okay. And then for part B, the force needed to accelerate the person in the circle, so we want to know what is the centripetal acceleration. For part C, we want to know what is their weight. That's the force of gravity. In part D, we want to know what normal force will be on the person. That will be their apparent weight. Now let's solve it. Now V, for part A, the velocity of this person is, well, how far do you go? You go around the circumference of the Earth one time. So that's 2 pi r. And how much time does it take? The period. So this is going to be 2 pi times r, which is 6.4 times 10 to the 6 meters, divided by the period, which is 86,400 seconds. And notice I'm showing my units and everything. This is going to give me a velocity of, when you round it off, when you punch that into your calculator, 465 meters per second. And that's my answer to part A. Now that's fast. If you're standing at the equator and you're moving around, you're hauling. That's like 1/4 of a mile a second. Okay, I'm going to finish this problem right now if you want to stay. It'll be about 5 more minutes. Now for part B. Shh. The centripetal acceleration, well, that's just going to be v squared over r. So that's going to be 465 meters per second. That's my speed. I'll square that. Divide it by the radius of the Earth. which is 6.4 times 10 to the 6 meters, or 6,400,000 meters. And when you do that, you get a pretty slow, it's not very big. Oh, wait a minute. Part B, I'm sorry, they don't want the centripetal acceleration. They want the centripetal force. Right? It says the force needed to accelerate the person. I'm sorry. So this should be the centripetal force. Well, the centripetal force, all I got to do is take this is equal to m times a sub c, the mass times the acceleration. The mass is 97 kilograms. That's the mass of the person. And it's times 465 meters per second, quantity squared, over 6.4 times 10 to the 6 meters. And what you get is a very small amount of force. I think it's 3, when you do the math there, it comes out to be 3.3 newtons. That means that you need a little tiny bit of force, net force, on this person to keep them going. Well, actually, the Earth would spin this way if this is the North Pole. A very small amount of force, 3.3 newtons. That probably weighs less than this, the weight of this remote control, 3.3 newtons. It's, not like that. Not very much. And so for part C then, well, the force of gravity, that's easy. That's just mg.
Attention, please. The AASU mandatory meeting is starting right now in room 302. The AASU mandatory meeting is starting right now in room 302.
And let's see, what do you get when you multiply? I don't have a calculator up here. You guys have one? Well, you know what? I think it's, I'll just use the answer in the book. 950? If I round it off, 950 newtons? Okay, so that's my weight. Now let's draw a free body diagram of this guy up here, okay, to get part D. Here's a curvature of the Earth, okay? Now way down here is this here, we'll make this the center of the Earth. And this person is standing right here. Now gravity is trying to pull you down. And that's that 950 newtons. You have a normal force like this. But here's what's going on. You need this 3.3 Newton force. You need a net force down, right? You need a net force down. Why do you need a net force down? Because if there wasn't a tiny net force towards the center of the Earth, what would happen to this person? You would fly off the Earth just tangentially to the rotation of the Earth. You would just go in a straight line like this. If you're going to go in a circle, something has to make you go in a circle, and that's that net centripetal force. Well, this is 950 newtons. This is approximately, well, it says 3.3. We'll just round it off to 3 newtons. So if this is 950 newtons, and we need 3 newtons left over, what's the normal force going to be? Well, it's going to be 3 newtons less than my weight. We'll say 947 newtons. And that's my answer for the normal force. If I want to be fancy about this, I'll say the sum of the forces in the y direction equals ma in the y direction. We'll make straight down towards the center of the Earth our positive y direction. Totally legal to do that. And so what I'll do is I'll have mg minus the normal force equals ma, which is 3.3 newtons, or 3 newtons. So if I add this to the other side, I subtract this to this, this is 950 newtons minus 3 newtons equals the normal force. which is 947 newtons. So that's going to be my normal force. So my normal force is slightly less than my weight. Now, people used to think there's no way that people could that the Earth could be spinning on its axis because people would fly off. Well, that's true if the Earth was spinning a lot faster than it is. But with this current rotation rate, the centripetal force on our person is very tiny compared to their overall weight. So they don't slip off the Earth. You stay. Now, but here's the thing. If you are on the equator, you feel slightly less in weight. Your actual weight is the same, but you feel slightly lighter. Why? Because of that, you need a net force towards the center. So the normal force is going to be slightly less than your weight. And the normal force is your apparent weight. That's what you feel. And so you will feel slightly lighter at the equator than you would at the North Pole. That is all. Thank you for your attention.